In this lesson, I'm going to talk about the normal probability distribution. The normal probability distribution is a continuous probability distribution. Therefore, it cannot be described in terms of a table where all the possible values of the random variable x are listed along with their associated probabilities. Because it's continuous, the probability distribution is actually defined by a function. In the case of the normal probability distribution, the function f of x, where x represents the value of the random variable, equals the exponential, which is base e, the exponential base e, to the power negative 0.5 times the quantity x minus mean, that difference divided by the standard deviation all squared. And then that exponential is divided by the standard deviation times the square root of 2 pi. It's a little harder to see here. It's not really that important in understanding the formula so much as realizing that the normal probability distribution is described by a formula. So again, exp stands for the exponential function base e, where e is Euler's number. The power of that exponential function is a negative 0.5 times the square of the ratio of the difference between the mean and the random variable divided by the standard deviation. So everything in here is the exponent to this base e. This entire exponential then is divided by the standard deviation times the square root of 2 pi. Now, since this normal probability distribution is defined by an actual function, it draws a curve, and the curve is called a probability density function. So this curve, the curve here that's defined by this function is called a probability density function. It's a curve, it's a graph. The way we find areas then when we're working with continuous probability distributions is to find the area under the curve that's defined by that function. Alright, so if I want to find the probability that some random variable is between two values a and b, I want the area between a and b as it's defined beneath that curve. This will make more sense when we look at an example. So let's look at the example, very common example for IQ scores. IQ scores are normally distributed with the mean of 100 and a standard deviation of 15. So we are given a mean of 100 and we are given the standard deviation of 15. Using this formula here, then I can replace x with different possible values of the random variable. The mean is 100, the standard deviation is 15. What I did is I wanted to get a graph of this curve so you could see how the function gives you the curve, and then we will find areas beneath that curve which represent different probabilities. Now I'll explain a little bit more in a minute, but it turns out that most of the data, as in 99.7% of the data of any normal distribution, is between 3 standard deviations of the mean. So if I take the mean of 100 and subtract 3 times its standard deviation of 15, I get 55. If I take the 100 and add 3 times the 15, I get 145. This will actually give me a range for 99.7% of the values. So what I did here then is I did construct a partial probability table just for the integer values between 55 and 145. So you can see if you go all the way down, it goes all the way to 145. I also then used the formula here to find the corresponding value of the function. So notice, here is the formula that we have written here, but I have replaced the x with the cell containing one of the values of the random variable. I replaced the mean with the 100, and the standard deviation with the 15, and then computed all these different values here for the function. I then went ahead and used the insert graph, and the graph I created was just one of these basic two-dimensional line graphs using x as the horizontal axis, f of x as the vertical axis. And when I did that, I got this function, this graph here. And so this shape here, this nice symmetric bell shape, is what we call a normal distribution. Usually it's referred to as the bell curve. Sometimes it's also called the Gaussian curve, named after the mathematician Gauss, who described it. Now, not every curve that is bell-shaped is a normal distribution. Normal distributions specifically follow the function that I've already described. Now notice right in the middle here, at this peak, is the mean of 100. And notice if I move 15 units, here's 115, that is one standard deviation from the mean. If I go another 15 units, this 130 is two standard deviations from the mean. Another 15 units to 145, that's three standard deviations above the mean. If I go to the left, down here to 85, that's one standard deviation below the mean. Another 15 units takes me to 70, that's two standard deviations below the mean. And then finally, three standard deviations below the mean takes me to 55. Notice at these points, 55 and 145, the curve is basically touching the horizontal axis, and that all these values then is 99.7% of the data is represented by the curve, and there'll be 0.3% that would just be just a tad closer on that end and this end, right? So here is that graph again, and what I want to talk about now is the empirical rule. Now, the empirical rule only applies to normal probability distributions. The empirical rule says that within one standard deviation of the mean, we have 68% of the data. So remember, one standard deviation from the mean here would be from 85 to 115. 95% of the data will be within two standard deviations of the mean. So two standard deviations within the mean is 130 and down here 70. So between 70 and 130. And then 99.7% of the data, which is virtually all of it, is within three standard deviations of the mean, and that's from this 155 to the 145, right? So we have the 100 minus 15, right, is the 85, and the 100 plus 15 is the 115. And let's find the probability that a random variable is between 85 and 115. What I'm basically going to do here is confirm the empirical rule. So the empirical rule tells us that there should be 68% of the data. So how can we confirm that? And at the same time, we'll see how we can find probabilities by using areas under the curve. We are told that 68% of the data should be between 80 and 115. So we want to find the probability that any value falls between 80 and 115, and that is found by finding the area under the curve between this 80 and this 115. To find the areas under a normal probability distribution, we are going to use the formula that's in the statistical functions called norm.dist for normal distribution. So here it is right there, norm.dist. Now, norm.dist only gives you the area to the left of a given random variable. So let me type in the larger of the endpoints, the 115. We're looking at a distribution with a mean of 100 and a standard deviation of 15, and cumulative means we need to add things up. We're looking for cumulative. And what we find here is that what I actually computed here, I should put it on this next line, because what I actually just computed is a probability that x is less than 115. Right, that's what I just computed. So let's actually put that in its proper place here. Okay, and I'm going to reduce some of these decimals. Alright, so we're looking at about 0.8413, 84%, about 84%, 0.8413. That actually is the probability of being less than 115. So from 115 down, it's this area underneath the curve from 115 down. Let's now find the probability of being less than the 85. So the probability that x is less than 85, what that's going to give us is this area from 85, okay, from 85 down. Alright, so from 85 down. So again, we'll go to formulas, more functions, statistical, norm.dist. And this time we're going to put in the 85 with the mean of 100 and the standard deviation of 15, cumulative true. Let's go ahead and decrease the decimals. And we see we have about 16% or 0.1587. Alright, so from 115, all this area here, that's 0.8413. 85 down is this area here. So if I want to find the probability of being in between these two, I would take the bigger area, subtract away the smaller area, and that'll just leave me the area in between. So we'll do equals area beneath 115 minus the area beneath 85, and look, we get 0.6827 or 68%. Okay, and so that actually confirms here this empirical rule for the within one standard deviation of the mean. Let's look at two standard deviations from the mean. So that's the mean minus 2 times the standard deviation to the mean plus 2 times the standard deviation. So look here, we're looking at 100 minus 2 times the 15, and there's the 70. And here we have the 100 plus 2 times 15, and there's a 130. We want to find the probability that a random variable is in between 70 and 130. Whoops. Okay, so we'll start off by first finding the probability that a random variable is less than the 130, the larger of the two. Okay, so from 130, that would be here and everything below it. So all the area under the curve up to the 130. So let's go to formulas, more, statistical, norm dist. Right here. And x then is 130. The mean is 100. The standard deviation is 15. Always write true for cumulative when doing probabilities for norm dist. And we get this very high probability here, 0.9772. Now let's find the probability of a random variable being less than the 70. So that will just be this little tiny area here. So the probability that a random variable x is less than 70, find that again by using formulas, more, statistical, norm dist. Norm dist. This time we are putting in the 70, mean of 100, standard deviation of 15, cumulative always true for this. doing norm dist for probabilities, and we get 0.02275, or here 0.0228. Of course, that's very small. So now to find the probability of being in between the 130 and the 70, we take the bigger area here from 130 all the way down, subtract from 70 on down, and that'll just leave us in between. So equals the probability of less than 130 minus the probability of less than 70. And look, there's 0.9545, or about 95%. We'll do this one more time for being within 3 standard deviations of the mean. And 3 standard deviations of the mean is between 55 and 145. Let's go ahead and do that. Well, we can do that up here. Okay, we'll do it right next to this one. So here we'll do the mean. Let's just go ahead and actually type things in. We'll go ahead and do 100 minus 3 times the standard deviation of 15. Right, there's that 55. And then we will do 100 plus the 3 times the standard deviation of 15. See, there's the 145. We'll do the probability that x is less than 145. So that will be formulas, more statistical norm dist. And we're doing 145, mean of 100, standard deviation of 15, cumulative true. Look how much that is, 9.99865. That's nearly everything. Then we'll do the probability of being less than 55. So again, more statistical norm dot dist, and this time we have 55, mean of 100, standard deviation of 15, cumulative as always true. And we see that's actually a little tiny probability there. And then to find the probability of being in between the 55 and the 145, we are simply going to do a subtraction from the bigger minus the smaller of the areas. And look, we have 99.73, 0.9973, or 99.7%. So what I've done is I explained the empirical rule to you. We confirmed it here by actually finding the values within 1, 2, and 3 standard deviations. And then I showed you how to use the norm dist to find the areas to the left, and then how you can do a subtraction to find an area in between 2 values. Let's do some more probabilities. We've done less thans and we've done in betweens, all in context of the empirical rule, but the methods are the same. We haven't done any greater thans. What if we wanted a greater than? So let's see. How about here? We see a 110. What's the probability that a randomly selected individual has an IQ score greater than 110? That would be this area in the right here from the 110. Well, remember, norm dist only gives you areas to the left. So if we were to compute then the probability that x is less than 110, we'd be getting the opposite of what we were interested. So when we do function statistical norm dist, and we do 110, and we still have the 100 and the 15 and true, right? This 0.74751, that is the probability of being less than 110. So that would be the probability of being here in the left side. We want to find the probability of being greater than 110, which is being on the right side. So how are we going to find the probability that x is actually greater than 110 rather than less than? Well, we're going to have to do that by doing a subtraction using the rule of complements. Recall that the probability under the entire curve is the sum of all possible probabilities for every element in the sample space, so that has to be 100% or probability of 1, right? We saw that what we're actually showing here from this 55 to this 145, okay, that is 99.7, but theoretically, you know, the whole thing, we'd get that extra 0.7%. So what we're going to do then is we are going to subtract the probability of less than 110 from 1. 1, which is the area under the entire curve, minus the probability of being less than the 110. So it's like starting with the whole thing shaded and then subtracting this 110, and notice that'll leave you just everything bigger than 110. So minus the probability of being less than 110, and here we get 25.249, or 25% of the data, or there's a 25% chance that a randomly selected individual would have an IQ greater than 110, which is the same as saying that 25% of the population has an IQ greater than 110. So whenever you want to do greater thans, you have to use the law of complements and do a 1 minus the norm dist, right? Doing a 1 minus. Okay, so that shows you how to do greater thans. Would the problem be any different if instead of saying being greater than 110, we want the probability that x is greater than or equal to 110? Would that make any difference? We know with discrete probability distributions it did make a difference, because that endpoint would add in some non-zero probability. So now the question is, how much probability is going to be added in by the equals to, by the probability that x actually equals the 110? Now, what we want to remember is that probabilities are areas under the curve, right? So when we had 110 being greater than or equal to was all this area. Or being greater than was all this area. So what about the or equal to? Well, the or equal to is just a line here, and the probability of actually being on the line is equivalent to the area of that line, and although the line has a height here or a length, it has 0 width because it's one-dimensional. Therefore, the probability of being exactly equal to 110 is 0. Therefore, the probability of being greater than or equal to 110 is exactly the same as being greater than 110. So we compute it the exact same way, and there is no need to worry about anything else. I guess I didn't copy this. Well, I don't know what I did wrong. But anyways, this probability would be the exact same as this probability. Oh, I see. See how it's changing from J1 to J5. But anyways, this would still be, let's just not worry about this. This then would be the same, the 0.25249. Okay, that would be the exact same probability of greater than 110, greater than or equal to, because the probability of being exactly equal to is 0. So I hope this helps explain what a probability density function is, meaning how it replaces a probability distribution table in the case of continuous probability distributions, right? Because we're working with continuous probability distribution. Right? So when you're working with a continuous probability distribution, what you have are probability density functions. For the normal probability distribution, we have a specific function here defined in terms of the exponential base e with an exponent that involves the mean and the standard deviation, and then that's divided by a value that involves the standard deviation again. When we're working with curves, then, since we have a graph like this, we define probabilities as areas under the curve. So that's why in order to find the probability of some value of x between two values, you find the area under the curve of that function between those two values. And then so we would have this normal curve and we'd find the areas underneath here, like we did here with the empirical rule using the norm dist commands. When we did, if you found the probabilities in between, you would have to do the probability of being less than the larger minus the probability of being less than the smaller. So you would have to do a subtraction. So it actually involves 3 computations that could be combined into a single one. So a norm dist for the larger minus a norm dist for the smaller. Right? In the case of greater thans, you have to, since the norm dist function only gives you probabilities of less thans, you have to do then first find a less than and then do a 1 minus the less than. And it doesn't matter if it's strictly a greater than or equal to, strictly a greater than or greater than or equal to, because the probability of being exactly equal to is 0, because we're looking at probability being areas under the curve. If you're actually equal to a value, that's just the area of a line which has no width, therefore no area.